And welcome to our random intercepts model discussion. So we're at the core of the class. We have done a lot of work to get ourselves here, but I think we are really well prepared to fully embrace the concept of random intercepts, and then in a couple weeks, the more challenging concept of random coefficients. And then we're going to build out some more implications of the model. We'll take it in different directions. We'll use these models, the fixed effects, the random effects, the fixed effects and random effects models in the context of longitudinal data, specifically 3-level models. We're gonna get some fancy tools here, but the core of these tools are the fixed effects stuff that we've studied, this random intercepts models that we're going to study today and next week, and then the random coefficients models in the next 2 weeks. And this represents really the core of the class. But let's take a step back, since we're here at the beginning of the core, or somewhere in the core. And think about where we've been. So at the first couple classes, we really highlighted the fact that we have non-independence of observations that we call nesting. So we have students nested in classrooms, and we expect that teachers and maybe other aspects of the classroom have an effect on students. And so there's a correlation between residuals of our models for students that are correlations between students that can be accounted for by the classroom effect. And so, and the same thing with persons, right? So we might have persons over time, and we think that persons are more related to themselves than they are to other persons, and that nesting problem is solved by splitting it into the between variance in the context of longitudinal data between persons or clusters, and then the within variance. Or in the context of students, right, you have the classroom effect, and then the student and the differences between students within those classrooms. But in those two examples, one the longitudinal example and the other the example of classrooms, we would expect different levels of a relationship between the between variance and within variance. And so in the case of classrooms, we would expect this interclass correlation measured by the between variance, which we represent as psi, and the within variance we represent as theta, to be a somewhat lower number. There's less between classroom, less of the variance is between classrooms than within persons, within students. Whereas in the person example, we expect the persons to have most of the variance, and people don't change that much. They change a little, so we would expect higher interclass correlations in longitudinal data than we would in measuring classroom effects. But nonetheless, we've taken this non-independence, we've split it into the between and the within variance. We can measure the proportion of variance attributable to each of those, and we call that the interclass correlation. We also discussed fixed effects modeling, which allow us to model the within effects, and we spent a couple of weeks on that. Some really exciting implications for fixed effects models for us, although they have some limited applications and some limitations that are not the same limitations as that the random intercepts models that we're going to discuss today have. We also discuss modeling the between subject effects through generalized estimating equations, where we take this non-independence, we model it as a covariance structure, and then we discard it, allowing the subject effects to be estimated accurately and the standard errors for those subject effects to be estimated accurately. So we've developed quite a bit of sophisticated tools for dealing with this data, and today we're going to fill out our pantheon of fixable problems. So I'm looking at this screen, and I'm sorry, I had to expand, I had to change the slides a little bit, so the slides that you guys have will work. Slides that I have were all messed up, and I didn't correct this. Anyways, moving forward, these models that we're talking about, sometimes called multi-level models, or hierarchical models, or I prefer mixed, fixed, and random effects models, blend the between and within effects. So in contrast to the fixed effects models, where we just are focused on the within subject variability, here we can model both between and within subject effects. So if you are interested in persons, and if you are interested in, for example, health disparities between racial or ethnic groups, those are fixed. Those are time invariant effects, and fixed effects models are going to have difficulty measuring those non-varying effects. Whereas the models that we're going to discuss today have no problem whatsoever. In fact, we have a lot of flexibility with that. Um, there, the fixed effects models that we discussed um, do a great job of controlling for all of those non-varying effects, although we can't specify them. Whereas the models today will allow us to specify them, but they don't adjust for ones that we haven't specified. So by saying that we're going to specify them, we have to specify them. If we don't specify some non-varying effect or varying effect, then our models are not going to be accurate, just like any model that isn't correctly specified is not accurate. These models are also going to be a little bit less functional in terms of generalized linear models compared to GEE models, and we'll talk a little bit about that. Although that will mostly come out in the complication of the conditional versus marginal model, which we're not going to talk about today, but we will talk about quite extensively in future classes. All right, so let's look at the model that we had earlier when we talked about the variance components. If you recall, we identified a zeta and an epsilon. The zeta represents the difference between the grand mean across all subjects and the individual's mean, which is represented here. And this difference between the grand mean and the individual and the group mean, the nested group mean, in this case a person, is represented by zeta. And then within person, we have a variance around the person mean, and that's represented by epsilon. And again, this combination of epsilon and zeta represent our total package of variance, but we've split it into the within and the between variance, right? Okay. So if we want to know whether we have nested data or not, we can use a variety of tools. We can use a likelihood ratio test to test whether the inclusion of a nesting factor is statistically improves the model. That's when we use maximum likelihood as an estimator. Or we can look at the proportion of variance between and within and make a more subjective judgment about that. And that's we have an ICC. And as I've talked to several of you, I'm not so concerned about low ICCs with some exceptions, and we'll go into detail about why that can potentially be a problem. But it's not a problem conceptually, right? It's a problem practically sometimes. But if you have any ICC, if you have any interclass correlation, it behooves you to adjust for it. Like in the models we run often in social science, if we can predict 20% of the variance, that's great. So I don't know why I would be concerned with only being able to have a cluster variance that accounts for 2 or 3 or 4%. Seems like a pretty high proportion of that, right? You can, at 5%, you're talking about a quarter of the variance that you predict is accounted for by the ICC. So I think that I'm tolerant of low ICCs, but sometimes we can run into problems, and we'll talk about that. Okay, so this is the model that we ran before, where we estimated the right meter effect. You've seen this data before. This is the average score. This is the variance between and within. So this is the between person variance, which is where most of the variance is, not surprisingly. And this is the within person variance. In the context of this variance represents our measurement error. If you recall back to that conversation where we talked about that, we ran a likelihood ratio test comparing this model to the null model that only estimated the mean and did not estimate these variance parameters. And we see that that's statistically significant, suggesting that we have significant nesting. The model is improved in a substantial way by adding this nesting component in there. Here we have the interclass correlation, which confirms what we just found. There, 98% of the variance is between persons, 2% of the variance is within subjects, suggesting a relatively low error rate to the inverse of this is the error rate. So that's about a 2% error rate. In terms of the measurement of the right meter, we get a pretty good estimate of a person's breathing ability. So all of this represents things that we have done before and brings us to the place where we're going to start today. So I want to use a new data example. It's one from the Sophia book. And I think that this allows us to really think through some of these issues that we like to think through. in a social sciencey, medically kind of context. So as you might be aware, there are people called mothers, and you might also be aware that sometimes those mothers smoke, and that smoking has implications for birth weight for babies. And that's what this data is looking at. So we have over 8,000 births for across about 4,000 mothers. Each mother in the data set has at least 2 births. We have a mom identifier called mom ID. We have a birth weight measure. It's measured in grams. We have a mother's age at birth of child. We have a race variable denoted as black, but the contrast, of course, would be white, which is the baseline. And then we have a variable indicating whether the mother smokes. One thing that I want to just call our attention to is at this point, we have, this does not vary within mothers, but that's okay. We don't want it to, right? This varies within mothers because each birth has a different birth weight. That's necessary for us to estimate a multi-level model. Otherwise, we don't have nested data. We only have data at the nested unit, not at the nesting unit. We have mother's age, and as I've talked before, age is a weird thing. Age is embedded in time and is completely collinear with time since we are all moving through time. So age is really a non-varying thing. Because we really have to measure age at a static level, or age can become our time variable. One or the other. We can't have a time variable in addition to mother's age variable. But here I think we're going to use mother's age as a varying effect in contrast to what I just said, because we're using it as our time measure. We have race of the mother, and this is non-varying. Some recent situations excluded. Most people's ethnicity stays fixed. And then smoking is whether the mother smoked at the birth of a child. So if a mother has 2 births, then she can smoke at the first and quit by the second, right? So there's varying answers to whether the mother smokes or not at the birth of a child. So the first thing I want to do is take some of the basic variables and reiterate those issues that we just talked about. As I promised you at the beginning of this class, we are constantly interrogating this question of within and between, because we have levels now, and if you get to 3-level models, right, you have within, between, between, and between. You just keep stacking the betweens and withins. But what you really want to do is think about, where does your data vary? Now, fortunately for us, Stata has some tools, and I know that I don't know offhand the tools in SAS and R for this, but I'm sure that they have them. So let's go to the data. So I'm just going to clear ourselves out here and open the smoking data. You should have all of this material. Now, because I'm going to use some of these XT functions in Stata, I have to identify it as a data set that's nested with nested in mom ID. And I can use this function called XTSum, which allows me to look at the effects between and within and separate out. It recognizes that I'm looking at multi-level data and lets me look at this. So you see here the mean, which represents the mean birth weight across all births, right? So irrespective of mothers, it's the mean birth weight across all births. This is the proportion of all births that had smoking, and this is the proportion of all births to black folks. So these means are just the means as if we had non-nested data. There's no trickery here. Where we start to see differences is in the variance, and we can see where the variance is. And the variance is the overall variance would be the mean minus the observations squared with the in the variance. So this is just the standard deviation, again, as if you had cross-sectional data. But we know we don't have cross-sectional data. We know we have data that is between and within separated, and so we want to look at the variance between and within. And here you can see that the between variance for birth weights is higher than the within variance. So that's already telling me something, that mothers are a big driving factor of the variance of birth weight, and that within mothers I would expect less variability than I would expect between mothers, and we've isolated that here. Um, so so we also see over here that we have this is the 8,000 births and the 4,000 mothers. Um, so so we'll talk a little bit more in a second about the difference between these between and within. I'll show you the formulas and we'll walk through them a little bit. But we can see also for smoking that we have an overall variance, but more interestingly, we have a between variance, and more of the standard deviation, I'm sorry, is between mothers relative to within mothers. Some mothers move from smoking to non-smoking or from non-smoking to smoking, but majority of the difference or variability in smoking is attributable to between mothers rather than within mothers. Not surprisingly, for black, we have no within variance. Mothers do not switch between black and non-black. All of the variance is located between mothers. And so this running these tells me something right away, that any effect for black is going to be between mothers, not within mothers. So this is the kind of variable that would not work well in a fixed effects model. If I was interested in the effect of race on birth weights and smoking, then I can't run a fixed effects model unless I were to think that somehow that effect changed over time, which is probably not true. I'm probably looking at something like disparities in health outcomes that differ across race, and I think that those are fairly static effects. So this would indicate that a fixed effects model is inappropriate, because fixed effects models, as we talked about before, model this within variance. So smoking would be something we could run in a fixed effects framework, and we can run the birth weight model in a fixed effects framework. If we did, we would control for all this between mother variance. All of that would be controlled for by the model, but we wouldn't be able to run black or race or any other non-varying coefficient here. So that's one thing that we can do to get a sense, is use these xt functions, and again, there's a corollary in R and SAS, I just don't know what it is off the top of my head, to really separate out the variance. Now, the other thing we can do is begin to look at the basic demographics of our sample and some of the other things. And one thing I want to call your attention to, and I'll call your attention to this before, is the idea that when we are dealing with nested data, sometimes we want just to estimate bivariate statistics or univariate statistics for the nesting variable. In this case, mothers are the nesting variable. So we want to know what proportion of mothers is black. In order to do that, we have to identify one mother from our data set. Now remember, the mothers are stacked on top of each other. Births within mother are stacked on top of each other. And mothers are also stacked on top of each other here too. But births within mothers are stacked on top of each other. And you can see that in the data. When you go to the data, we have mother 14 has 2 births, or 3 births here. Mother 25 has 3 births. And I don't want mom 14's race, race, what is she? I think there's only black and white in here, right? So mom 14 is black. I don't need 3 blacks. I just need to know mom is black once. That's all I want. So that's what I'm going to do, is I'm going to select one mom, and I'm going to do that in Stata. And all of these programs have indexing capabilities, and it's fairly easy to figure it out. If you need help, I can tell you how to do it. Where I say egin one child, and that's just picking one child. And incidentally, it's going to pick the first one. So if it matters which mother is selected, so for example, if I were interested in when I want to find the age at first birth, right? If I was interested in the age at first birth, then I would need to sort my data by mother's age. So I have the first birth at the top. So you need to pay attention to sorting here too. And so I run this, and that gives me a variable that just identifies one child per mom. It's a simple variable that is 0, 1. And as you can see, these first 3 are mother 14, and it just identifies the first one. The same thing going all the way down, right? Turtles. So here we're just going to estimate black, and we used the sum function rather than the tab function. We can use the tab function as well. one child equals 1. Sum gives you the proportion. When you sum a bivariate, when you sum a dichotomous variable, it gives you the proportion. So 7% of the mothers are black. You can see that too if we were to do this. You can see that this number represents 7.14, right? So you get the same answer here. So that tells us what proportion of mothers are black versus white. If we also wanted something like the number of children per mother, we can count the number of births, per mother, by estimating this. We actually right. So I think I need to do. I need to do this. I think I need to do by sort mom ID to get that. And then I just tabulate the number of children. Now, if you look at this, right? So this is 3, this is 3, this mother has 2, this mother has 2. They're all the same, again, within mother, right? Because I just counted up how many births are within mother. And now I can tabulate that, and I get an answer that the majority of the sample, the vast 83% of the sample has 2 births. A smaller chunk of the sample has 3 births. And so I can know things about my nesting structure. I can know things about my individuals, but I have to pay attention to that now because I have nested data, and I want you to think through that as you think through your variables. If the variable is a variable that doesn't change between mothers, such as black, well, then we need to select one example of that because there's no variability within. So for the mothers that had 3 births, we would get 3 blacks for them. Well, we don't want that because we don't need to weight these mothers at 3 and this mother at 2. That makes no sense. So we need to think about what is varying and what is not varying with our data. All right. So we've done a good job assessing our between and within variance. And I want to just take a little bit of a second and walk through what these variance pieces mean. I know that this is tedious and often confusing, but I think that the important piece here is that we begin to think through what it means when we say between and within in very practical terms. So overall is the standard deviation of the grand mean from each observation. So this is that overarching mean. If we think back to this figure right here, this is our grand mean. It's the mean over all of the observations. This is the deviation between our group and the grand mean, and these are the deviations between our group mean and the individual observation. And we're just going to separate all those out in terms of the between variance and the within variance here. All right, so we can see that in the equation, we're summing up over all of the groups, all of the nesting units, and we're summing up within the nesting units. So that is this n sub j represents the number of clusters. So some moms have 3 births, some moms have 2 births. So this will be from 1 to 3 for the mothers that have 3 births, and it's 1 to 2 for the mothers that have 2 births. So over all the mothers, within all the mothers, we take each individual observation and we subtract it from the grand mean. This is your classic standard deviation. This is the standard deviation formula you learned before. We've separated that, as you know, into the between and within. And the between variation takes the variance between the group mother means. So this variable right here is the mean of mothers. So if you think about that table that we have here, where we have the grand mean, right? And then we have individual observations, and we have a group mean. That's a terrible location of that group mean. It's the variance of these group means that is represented by, this is that group mean, and then it's the distance between the group mean and the grand mean, which is represented by this number. And those are just summed up and taken in the classic formula for our standard deviation. So the between variance is the variance between, in this context, mothers. The variation in weight between the average birth weight for a mother. But those mothers also have varying birth weights within themselves. And that is what these individual observations are. So now we take, if we just, let's just take this and blow it up bigger. So we have the two births, and we have the mother's mean, right? So this is the mother mean, and this is our zeta here. These differences are our epsilons, and it's the variation from these points around the mother means, right? So these are the individual points, and this is the mother mean. We just talked about that up here, right? And then we, working over all the mothers, within all the mothers, we take all of that, and that is the within variance. So again, we've split the variance into the between and to the within component. Now, we've done a number of things to check our multi-level data, and while you learned how to do this stuff for cross-sectional data or flat data or non-nested data, there are some nuances to data that is nested. So for certain things like demographics, where it's non-varying within groups, you need to select one observation in order to not have multiple observations. So if I was doing something on classrooms and I wanted to get the and I was interested in the years of education the teacher of the classroom had. Well, that doesn't vary between students. All students are dealing with one teacher. The age of that teacher is the same for all students, right? There's no weird relativity theory thing going on with the age. All students experience the teacher's age the exact same way. And so I just need to select that teacher for that classroom. I just need one observation from that classroom to represent that, just like we did with one observation to represent the race of the mother. We don't need 3 observations for some mothers and 2 observations for other mothers. And so you need to select one unit and get whatever the univariate statistics you're looking for that one unit. We need to check the number of nested units to just make sure they are what we think they are. In the class, we've talked a lot about sample size requirements, and we will continue to do so. But you want to think about the fact that we're using the means of these groups quite frequently, and so we want to make sure that we're able to accurately estimate the means for these groups. Now, you don't have to have, the good thing about random effects models as opposed to fixed effects models is that we're borrowing some information from each other, and so we're in a little bit better place when estimating the means because we make assumptions regarding the normality of the distributions, and we'll talk about that in a second. So, but on the other hand, you want to at least be clear about where your weaknesses in your data are. We want to check for differences in the between and within the frequencies, means, and variances. We want to have a sense of what kind of variability we have in our data, and that will tell us something about how much we can play with, and we'll talk a little bit about that toward the end of class today. And in case you didn't want to pay attention to this whole slide, you need to check the variables that change, check the variables that don't change within cluster, and you have to know how much they change. That's the take-home message from the univariate statistics. And as you guys begin to play with your data, I look forward to seeing how that works with you. So this is the stuff that we saw before. I jumped ahead and showed you the Stata output, but this is the same things that we just saw before. There are some other features in XT mixed. I don't know in Stata. So here's separating out this is the tab function for it, and it separates out the between variance from the percent of within variance. So this is the percentage of mothers who ever had a smoking episode during any of their births, and this comparison is the number of 80% of mothers who ever smoked at every birth. 95% of the mothers who didn't smoke at all the births. So these tell you the proportion of, this tells you how much variability you have within smoker or non-smoker. So basically non-smokers have a 95% chance at any one birth, have a 95% chance of being non-smokers at all births, whereas 79% of the mothers who smoked at a birth had a probability of smoking at all the births. So that's what's separated here in the within and between. There's a whole bunch more of these kinds of tools, and I think that as you begin to think through your data, you really want to think clearly about where the variability is and where you expect it to be. We now have two sources of variability. All right. So let's take a null random intercept model and think about it. So the model here is the model that we saw before, the one that we call the variance components model, where we have a grand mean that's represented by our beta naught. We have a zeta and we have an epsilon. Let's just review what all of those mean again. Here we have the overall mean. That's our beta naught. Here we have a difference in the group between the grand mean and the group mean. That's our zeta. And then we have a difference between the group mean and the individual observation, and that's our epsilon, right? So each of these things are present in our model. We've split the variance, we've split the mean, we split each individual observation now as three components: the variation from the group mean from the overall mean, and the overall mean. Those are the three components that we currently have. We can look at it another way. So this flips it a little bit and makes clear some of our assumptions. We assume that these are, that line was a really bad job of drawing the line there. I can't do it. I'm going to keep failing if I keep trying. So we have a normal distribution both around the grand mean here and our group means. We are assuming that these are normally distributed. And when I say borrow information, which is what I was talking about before when I said we're less concerned with the sample size within cluster for multi-level models, because we're borrowing information. We're assuming that these are normally distributed. So we walk into the situation knowing something about these zetas. So when we estimate the zetas, or the variance of the zetas in the case of most of our models, we're not freaking out so much about the fact that there's only two bursts, or etc. If we were looking at a fixed effects model where we had stripped out the mean of the group, well, then we're a little bit worried about the number of observations within unit that we have, because we want to get a good estimate of the mean. We're not borrowing any information from anybody else. It's only the individual estimate for each person that is represented in the fixed effects models. Here, because of our model-based assumption that these are normally distributed, we have some helpful information that we're drawing on. The same for our errors that vary within person, right? So these are our within person or within class, whatever cluster unit variance that we have. And again, we're assuming that these are normally distributed around the group mean. So we have two different normal distributions. This is what we've almost always assumed, right? Almost all of your other models, you assume that often we think of it as the dependent variable has to be normally distributed. That's not true. The error term needs to be normally distributed. It's just that the error term distribution is often very strongly related to the distribution of the dependent variable. We have two normally distributed constructs here. One, the variance of the zetas around the grand mean, and one, the variance of the epsilons around the zetas. So again, we've split it into the between and within. We have a variance of each. We assume those variances are normally distributed. Here's the breakdown of that again. Just calling your attention to the fact that we don't see the zetas and the epsilons. What we're going to see in the output is a variance parameter for the zetas and the epsilons, and we call the zetas variance psi and the epsilons variance theta. And I will note that this fact that we are not getting things in themselves like we are here. Here we get a mean. That mean has a standard error, but that is the standard error of this mean. Whoop. That is the standard error of this mean. This variance is the variance around the variance of these guys around the grand mean. And it's because we are estimating a variance with the same distributional assumptions, right? We made assumptions about distributions of that. It's that distributional assumption that gives us the random effect. That's why we call this a random effect. I will note that you have always dealt with random effects because this guy has always been a random effect too. It's just we never called him a random effect in regular OLS regression. But once we get two of them, we sort of have to name them now. We call them random effects because we are looking at a distribution around a population rather than a thing in itself. This is a mean. This mean has a precision, which we measure with the standard error. This has a precision too, but that's not what this is. This is the variance of these guys around the grand mean. So that random effect piece is really about this, and why I like to call these mixed, fixed, and random effects is because we have fixed and random effects in the model. We have both fixed and random effects in the model. Alrighty, so let's estimate that basic model using our birth weight data. And here we see we have the average weight. This is the weighted mean of the mother's means. It's about 7+ pounds on average per birth. Here we have the variance components. We have the variance of the between mothers and the within mother variance. And what we can see here is that the between mother variance and the within mother variance there's a pretty close relationship. These are standard deviations, not variance terms. When we square them, that difference will get bigger. But no, they're pretty tight. They're pretty close. We can estimate how close, right, by doing our interclass correlation, and it's about 0.49. Stop that rounding, right? And so about 50% of the variance is at the mother, about 50% of the variance is at the birth. So there's quite a bit of variance in each location. There's a lot of stuff for us to play with. All right, now I want to call your attention to another aspect of these models that we have not really highlighted so far. This zeta, so this term right here, we consider this a residual, the error term. Everyone knows what that is. We only leave it over here. This zeta, though, is often referred to as here, I'm calling it a random intercept. So this is the intercept for across everyone. This is the intercept for each mother. So when I say random intercept, what we are allowing is a random variable characterized by the distribution to specify a separate intercept for each mother. And we can see that by just moving that zeta over here. And for each mother, we now have their individual intercept. So each mother is allowed to have her own intercept. These things over here are our covariates. And the combination of these two things we would call the mean model, because we're literally modeling a mean. And each mother has her own intercept, and then these components are added on. And from that, we can get the expected value for each mother based on the characteristics. And then this term represents the difference between the expected value, which we would characterize like that, and the actual value, which we characterize like race pen, like this. Okay. However, we can also think of this over here, and we often, when we characterize them, we group these together because these are both characterized as random variables, whereas this is a fixed effect. So we can think of this zeta either as a complement to the error, or which is where we started the class, right? We talked about the error term, the psi, I'm a terrible, psi ij, right, is comprised of the zeta sub j plus the epsilon ij. right? So we can think of also as this, it doesn't matter from a mathy point of view. It doesn't matter whether you add something at the beginning or at the end, right? So, but conceptually, I just want to call our attention to the fact that we're thinking of these in multiple ways. Sometimes we think about it in conjunction with the error term. Sometimes we think about it in conjunction with the intercept. It makes no difference from a modeling point of view. It's just conceptually when we talk about these things, we move them in both places, and I don't want that to confuse you. I think it's a pretty straightforward thing. All right, let's talk about some of the assumptions that we have in these models. And this is, in the past, I think I've done a particularly bad job of describing these assumptions. I'm hoping to do a slightly better job this time by tying them to the assumptions that you've already known and just drawing them out a little bit. So you are familiar with the independence assumption and the homoscedasticity assumption, and that's the assumptions that we're going to basically identify as part of this. There's a lot of nuance to this that I'm not covering that the Sophia Rebheskes book covers, but I think it's all pretty derivative of this. If you understand these basic ideas, you'll have the basic ideas that we're gonna talk about in terms of the assumption. Now, independence can also be referred to as exogeneity, meaning that it's on the outside of the model rather than on the inside of the model. And independence is a more strongly worded way of phrasing that assumes normality of distribution. And the Sophia book, and I think a lot of modern authors refer to this as exogeneity, because we're not, the normality assumption is a little overplayed, and we're less concerned with it than you certainly have probably been led to believe. But the exogeneity stuff is no joke. And what I mean by that is quite literally that, so first is sort of a mathematical necessity by how we get this. After conditioning on the x's and conditioning on the zetas, the epsilons have a mean of 0, which is pretty hard not to do given how we've constructed them. But importantly, there is no correlation between the epsilons and the x's after we've conditioned on these guys. After accounting for these guys, there's no correlation here. And that's a pretty strong assumption. In fact, you'll note that this is the exact problem that we are solving by using multi-level modeling. What we're saying here is we actually have to solve the problem. We can't just wave multi-level modeling. We just can't wave proc mixed at it and hope that the problem goes away. The problem has to actually go away with our nesting structure. Our nesting structure has to be the actual nesting structure. So in talking with some of you guys, you've identified additional potential nesting. So maybe you're looking at schools, classrooms, and then students over time. Well, you're like, do I have to really estimate the effect of schools? And maybe if you still have a correlation, if the epsilons are still correlated, and by the way, the epsilons cannot be correlated with themselves over time either. If there's still correlation between the epsilons, then that's a problem. If there's still correlation between the epsilons and the x's after conditioning on these guys, then that's a problem. We are assuming that this correlation is equal to 0. Likewise, we assume that the expected value of the zetas conditioned on the x's is also 0, and that the zetas are not correlated with the x's. You will note that when we did the structural equation model the other day, I pointed out that we had the alpha, right? And then I correlated the alpha using the arrows like this with the x terms. I allowed those to be correlated because your x's are all allowed to be correlated with each other in the model, and the alphas are really just other x's. Let's just keep it consistent with what we have here. The alphas are really just other x's, and the fact that we allow those x's to be all correlated is what allows us to deal with the issue of non-varying variance and controlling for it. That's why they're able to control for it, because they adjust just like all of the other x's do to each other's presence by modeling that correlation. Here, we cannot allow this. Those correlations have to be fixed to 0, and that's what we're saying here. So that's a pretty restrictive assumption that the zetas are not correlated with any of the x's. Let's just stop and think about that for a second. If we have a zeta that is mother, in this case the zetas are mother, then we're saying after we control for the x's, the zetas are no longer correlated with any of those x's. They're no longer correlated with age. They're no longer correlated with black. They're no longer correlated with any of the other covariates because we've controlled for the covariates and we've adjusted for the adequate, and the nesting has solved our issues. So we're making a very specific statement there. And as we go through the class, we'll identify ways in which we can look at that explicitly and see if that's true. There's both fixed effects, there's both standard approaches that we will learn next week, and then there's also approaches that we've learned with the SEM approach that we can use to identify those potential correlations. And so we're not gonna have to take that on faith. We'll be able to look at that, and then there's a variety of tests that we can use to model that as well, and we'll talk about some of those next week. So in addition to the exogeneity assumption that is familiar to you, we also have the homoscedasticity assumption that is familiar to you, that the variance has to be represented by a single term here, that the variance of the epsilons, that the variance of the zetas has to be represented by a single term, and that there is no correlation between your epsilons and your zetas. Those have to be, they have to be independent of one another and cannot be correlated with one another. And so those are all pretty strong assumptions. Now, I will note that a lot of this homoscedasticity assumption pops out in the form of biased standard errors that we can adjust for using the sandwich estimator and robust variance estimators that we talked about before. You can use those same robust variance estimators, certainly in Stata, and I believe in R as well, although I'm not sure in SAS, and address homoscedasticity concerns. So there's ways to deal with that. Bootstrapping is another approach to this. So there's a variety of ways we can deal with it if this problem exists. It's suffice to say that this is an assumption that we continue to have. The other assumption is that the covariance structure of the residuals is correctly specified. We'll spend some time in this class talking about that, particularly when we talk about longitudinal data. When we looked at the SEM model, I also want you to note that we had those error terms, right? And I said that we fixed them to be the same across the 3 different time points that we had, but that the SEM model didn't want to do it. It wanted to allow them to vary independently. And so so we can play with this idea, but the standard model assumes that the residual structure is similar across all observations, that we have one epsilon variance estimator, which is theta, and that we have correctly specified those residual correlations that we talked about with the generalized estimating equation model appropriately as well. And again, we'll have some ability to modify that, but we have to pay attention to that. The mean structure that is correctly specified, that means that we've got the right covariates in the model and they're specified correctly. The distribution of the residuals is normal, or at least symmetric is really what you're looking for. Not symmetric.ic, but symmetric. And so, and then one more that I really should have here is the linearity assumption. We are making very strong linear assumptions, and there's some difficulty in making those interpretations accurately. Once we get to the place where we're now ready to do some parameter estimates and estimate various parameters, we start with the intercept, and so the beta is the mean of the cluster of means, as I mentioned before when we talked about the birth of the mother. It's actually the mean of the means of the zetas, right? Those are our means, and so it's the mean of the zetas, and the when in unbalanced cases they're weighted, so it's the cluster of, it's the mean of means, and in this context, note that the estimated standard error of beta is going to be greater in the random interceptor or the variance components model than in OLS regression due to the accounting for the clustering. So in general, we increase our standard error a little bit of our beta because we've grabbed some of the information and put it into the mean as opposed to having each of the individual observations. But we think we get something of value out of that, which is why we're doing it. In terms of the other covariates, this is not going to be very different in a base way from the way that you've been interpreting regression coefficients so far. I think the coefficient interpretation of fixed effects models is really much more complicated than it is in random effects models, certainly in random intercepts models. Random coefficients models will add a twist to this. But in random intercept models, the interpretation of your parameters is basically the interpretation of your parameters that it's been all along. So the stuff that you learned at the end of your first year stats class is going to be the same thing that we're doing here. Ignoring clustering is not the right idea. We've all covered that already. And the one complexity that we're going to have to deal with is the between and the within cluster complexity. So we have to pay attention to what varies between and what varies within, and what we're talking about in terms of between and within, and we'll add some complexity to that today. So let's think quickly about what we do when we add a covariate in a random intercepts model. The intercept represents the point along the y-axis where the slope of the line intersects it, right? This is our intercept right here. By adding an intercept for each mother, we're allowing this line to vary. What is not varying currently is the estimate around these lines. The slope of the line, you will note the distance here and the distance here are fixed. They are the same in these current models. This is incidentally what we will loosen up in the random coefficients model. But currently, for the random intercepts model, the distance there and the distance there is exactly the same. We have just shifted the line down a little bit, allowing for different guesstimated weights of births for mother, and that's the effect that we get out of it. So we're now modeling each mother's slope at a different location along the y-axis, right? But the relationship of x and y stays the same no matter, because you can see the slope of the line is consistent across the board, right? It doesn't matter where you are along this x-axis between these two mothers, the slope of the line is the same, and this here would represent the statistical test, right? The line has the slope of the line has an estimated standard error, and that's what you're seeing here with these normally distributed these normal distributions around the slope of the line. But they're all the same, no matter where you are along the mother. So the point here is that the coefficient interpretation, by the fact that we're adding lines in a parallel fashion, doesn't change. Now again, random coefficients are going to change that for us, but with the random intercept model, no matter where the mother is, the slope of the line is going to stay consistent across all of that. And so the interpretation of our parameters, which are slopes, is exactly the same. So if we add smoking, for example, to the model, we can interpret this as smoking is a 0-1 variable, right? So as moms move from smoking to non-smoking, you would expect the birth of their child to go down 278 grams. All right? So as we move from non-smoking to smoking, because 1 is smoking and 0 is non-smoking, we have a coefficient, we have an expected decrease of 278 grams for the birth of the baby. So that is the isolated effect here in this model for the consequence of smoking. Now, to get an estimate for a non-smoking mother, right, that's this right here. The estimated birth weight for a non-smoking mother is 3,500. The estimated birth weight for a smoking mother is, what is that, 29 something or 28 something. So we, no, I'm sorry. I'm being overly pessimistic, about what, 3,300 grams. So to calculate we can calculate now two means: the mean of mothers that are not non-smokers, have never smoked. That's this. I keep doing that. And then this is the effect of smoking. I've been a little vague about that because I told you these are within and between separated. We'll get back to that in a second. But let's talk about another issue. We have these two variance components, and we have used these variance components in the past to calculate our interclass correlation. However, we have sucked up some of the variance here. We have captured some of the variance, and it can come from here, or it can come from here, or it can come from both. Probably comes a little bit from both in general, but you know, it's certainly coming out of this pool. So this is no longer an interclass correlation. What this is a residual interclass correlation. If you look at, we looked at this earlier when we looked at the assumptions, and I said that we assume that theta is the variance of the EIJs controlling for the x's and the zetas, and the variant, then psi, the variance of zetas, is this variance of zetas controlling for the x's. Now when we don't have any of those, this is just the variance of this, and this is just the variance of this. But when we do have x's, that conditional statement matters. And so now the interclass correlation is no longer just the variance of the within and between, but it's the variance of the within and between with the variability that is contained in the x's taken out of them. So this is the residual variance, right? You see me moving between the mean and the error model that we discussed before. We're doing that right here. We're now thinking about it more in terms of an error model. Here I was thinking about it more in terms of a mean model, but the error model here is the proportion of remaining variance after conditioning on the x's, in this case smoking, that is at the mother level versus the total level. So this, you'll notice that the interclass correlation in the raw model was 0.48 or 0.49, somewhere in there. And now it's 0.46. So it's gone down. The proportion of variance attributable to mothers has gone down, in part, and not surprisingly, because we've captured some of that variance in the form of smoking. We've modeled some of that variance directly with a fixed effect. And so it's come out of the variability that remains, that is accounted for by our random effects models, by our variance components. So we sort of lose the ability. You should be cautious with the interclass correlation. When you say interclass correlation, what people mean is the interclass correlation in the null model. But when we have two models, we can compare the change in variance between those two models, and we call this R squared. And in the context of the work that we're doing here, R squared is pretty easy to do. You would take the variance from the original model, the total variability from the original model. You'd subtract it from the variability in the new model. So how much difference is there between the new model and the old model? And then how much of the variability that was available, which is the variability in the old model, was captured by the new model, which is represented by that difference. So the R squared here is interpreted the exact same way, the proportion of variance attributable to the model. And we estimate that by taking our variance components in the new model and in the null model and subtracting them and placing them over the null model. So that's how we get the R squared. And so we can look at the proportion of variance explained by the model relative to the null model, where we can calculate the interclass correlation. All right. Now, nobody here runs models with one covariate. We use multiple covariates. And here we have our regression equation, including a number of covariates, where we still have smoking. We have whether the baby was male or female. We have maternal age, which is a time varying variable in the sense that it is the variable measuring time. Some people, like my wife and I, can't figure out how to have babies until we're really old. And so that's going to have an effect on birth weight, whereas some folks have babies when they're really young, and that's going to have an effect on birth weight. And then there's an optimal age for births, which is somewhere in the middle. But what the data says here is that older mothers have heavier babies. Now, again, we're making the assumption, because this is a continuous variable, that there is a linear relationship, and I will put money on it that the older mothers, that there's a curvilinear relationship here, and if I were interested in this topic, I would be exploring that curvilinear relationship and not assuming linearity. We're going to spend a whole class on that. Here we also see evidence that being a high school graduate increases birth, having some college increases birth weight, and having a college degree increase birth weight, all compared to having no high school degree. Now, do I really want no high school degree as my baseline? Probably not. If I'm doing that, I'm probably putting high school grad as my baseline here. But that's just me, right? Being married increases the birth of children, and that's probably related to socioeconomic effects. Being African American lowers the expected birth weight, or being black in this context, it may or may not be associated with African American. African American and black are not the same thing, but we can't distinguish those differences here. This is some measure of birthing stuff. I don't know exactly what it was. These are measures of prenatal visits. So mothers that have no visit have lower birth weights than mothers that have one. Mothers that have two visits have higher birth weights than mothers that have one visit, and mothers that have three birth weights have mothers that have three visits have higher birth weights than mothers that have one birth weight. So again, we have to pay attention to what our baseline here is. And so there's some interesting facts there. I don't really, this isn't my area, so I don't have a whole bunch of super important findings here, but it does seem consistent with a whole host of things, including the importance of prenatal care for births. Here we have the remaining variance. Again, we would not calculate the interclass correlation, but we could, if we wanted to, take these parameters and the original null model and calculate the change in variance between them. How much of a reduction in variance was there between this model and the initial null model that we ran? So we could calculate an R-squared for this if we were interested in it. So I want to focus on the smoking variable, because as I mentioned before, there is a problem with the smoking variable in that it represents the coefficient for change in weight between mothers that smoke, right? So there's a between variance there. And it also represents the coefficient for the change in weight of births between births of mothers that change on the smoking variable, the within. So we have in this variable, this coefficient includes both the within and the between variability, and that's probably not what we want. We probably want to have some sense of, and if you think about the public health implications of this, if a mom quits smoking, does that help her, or is she sort of screwed if she's ever smoked, right? Does ever smoking change it? Does smoking at all change it? The other piece of this is that mothers that are likely to smoke are probably likely to do other things that aren't included here, like drink or have poor diet or other things, right? So caring for one's health is probably strongly correlated with smoking. So smoking, the variable smoking, is capturing more than just whether somebody inhales smoke from cigarettes. It probably includes a whole bunch of things related to lifestyle choices. And so so the good news is that we can separate these into the within component, which is the fixed effects component, and the between component. How do we do that? Well, we do that. There we go. We do that. What happened to my models? Stuff here got all mixed around. We do that by doing a little bit of mathematical magic using stata. You can do it again in all of the applications. Is I take each of the moms, that's by sort mom, that's what that means here. And again, R and state and SAS have their own way of doing this. But then I calculate a mean for each mother. Incidentally, and I don't know how to do it in R. I know there's ways to do this. There's probably an application that helps you do this. But in SAS, I would use the proc mean function with a by variable for mom ID, and then output that as my data, and then merge it back in. There's probably other ways to do it, but that's how I've done it in SAS. So I take moms, I create a variable called mean smoking, and I get the mean of smoking within mom. So this is the mean of whether mom smoked or not. So what this variable is the proportion of bursts that a mom was smoking. So if a mom smoked on all 3 bursts, the value would be 1. If a mom smoked on 1 out of 2 bursts, it would be a half. If the mom smoked at 1 out of 3 bursts, it would be 0.33, right? So it's just a proportion of bursts that a mom smoked on. And then I take the deviation from the mom mean. So this tells me how much the mom changed from their mean. So it'll be, if the mom smoked every time, this is going to be 0. If the mom smoked no time, this is going to be 0. If the mom smoked sometimes but not other times, the proportion of what they smoked relative to the individual observation would be the value here. So if mom had 2 births, she smoked on 1 birth and she didn't smoke on the other birth, this variable here is 0.5. So this variable here would be 0.5 because it would be 0.5 or it would be negative 0.5, right? So 0.5 for the birth where she is smoking, and negative 0.5 for the birth where she is not smoking, right? Okay, so I just calculate that. I'll show you these variables here in a second. So again, we have a mom here. She had 2 births. She smoked at both the births, so that is 0. Here's a mom that had 2 births, smoked at this first birth, and then quit smoking, and so she has a -5 for this and a 5 for this. This mom smoked at both births. These other moms smoked at no births, right? This mom had 2 births, smoked at 1, quit smoking, same as before. So we have a sense of there's some variability, but not a whole bunch, right? So this mom had 3 births. She smoked, and wait, she didn't smoke, and then her children drove her to smoke, and so she started smoking. Here the opposite effect again. The mom smoked for the first birth but not the second birth, etc., etc., etc. So now we've isolated the effect for the mean effect and the deviation from the mean effect, and so we can split those two, and we do that by just putting these 2 variables in the model instead of smoking and estimating our model. And when we do so, we're going to be able to look at how much of the effect on birth weight is the fact that the mom smoked versus the fact that the mom, or how much expected value can we get from quitting smoking versus how much is just baked into the fact that the mom smokes. So here we see that changing from smoking to non-smoking, right, because going up is going to be associated with more smoking, decreases the birth weight. So picking up smoking decreases the birth weight of babies. But ever smoking, regardless of whether you quit or not, for subsequent births, also decreases smoking. And so there's pretty clear evidence here that never smoking is the best option, that any smoking reduces the birth weight of babies, even if there's a change in whether the mother is smoking at that point in time. And again, we haven't isolated the reason for that, and I don't know what that is off the top of my head. I imagine that there's probably a whole bunch of things that are indicated for by smoking here. For example, we don't have socioeconomic status. We don't have regionality. We don't have a whole bunch of things around lifestyle choices that I bet you smoking is confounded with. So all of those confounders are being sucked into the smoking variable. So we're seeing more than just smoking here. But I think that what we've seen here is the ability of these models to split the between and within into its components parts by separating them. And we can only do that because we have a random effects model. This is not something you can do in fixed effects model because this is exactly the thing that's taken out. We couldn't ask this question in a fixed effects model. We can only ask this question in a random effects model because we can separate and model directly the between and within effects. So we're going to be spending the next couple weeks talking about this. Certainly next week we'll spend more time talking about this in detail, and we'll look at how we can evaluate the fit of these models and test some of the assumptions and dive in a little bit deeper. But this is the basic idea of random intercepts models. Take care.